Yes, let's start now. Bismillahirrahmanirrahim. Experiment number 4, Joule's equivalent of heat. Joule, name of the scientist, and Joule's equivalent of heat means we will be converting electrical energy into heat energy, and we'll find out a constant. We would call it Joule's constant. The objective of today's experiment to study the relation of electric energy to heat energy using an electrical calorimeter. So this is your device, and we are to convert electrical energy into heat energy. And when we say that electrical energy is converted into heat energy, keep in mind that the unit for mechanical energy or the electrical energy is joule. Okay, and the unit for the heat energy is calorie. And there is a relationship between these two units, and we have 1 calorie is equal to 4.184 joule. And the ultimate objective of today's experiment is to find out Joule's constant J, which is equal to W over Q. W is the electrical energy, and heat energy is Q. Okay, and Joule's constant J. We will be finding out this constant with the help of our experiment today. We have the real or the standard value for J. And finally, we will compare these two and would find out the percentage error in the measurement of Joule's constant J. The apparatus you need a digital voltmeter and digital ammeter. One to measure the potential difference in the unit of volt, and the second one, digital ammeter, to measure the current through the circuit. And digital voltmeter is connected in parallel with the resistor here. And ammeter is connected in series with the circuit. This is the switch. If we close it, the current will pass through the circuit, will flow through the circuit. Okay, so the ammeter always in series like this one to measure the current flowing through the circuit, whereas the voltmeter is connected in parallel to the resistor. You have electric calorimeter, so this arrangement is called electric calorimeter. You have a cup with the lid. This is the lid. The cover of the cup. This is the plastic insulation material, and we have heating element. Heating element or heating resistor. Okay, and you have here this temperature sensor, the thermometer over here. We insert it, okay, so that it is dipped in the water. Okay, and this is the stirrer, like your spoon in the coffee cup. What you do with the spoon when you are having coffee, you stir it with the stirrer with the spoon, so that you have same temperature throughout the cup and you have the same sugar level throughout the cup. So you stir it with the spoon. Similarly, you have this stirrer today. You will be moving it up and down so that you have the same temperature throughout this cup while heating. This is the switch here. You have the power supply. This one power supply. You have connecting wires. You need connecting wires to connect all components. You have 750 USB interface. And you have computer. This is the experimental arrangement. As I told you, you have this calorimeter. See, you have in fact two heating elements. We connect them in series, and you have two connecting ends. These two connecting ends, you connect a voltmeter over here, parallel, and you connect ammeter in series. What we do, one end of this is connected with the one end of the element is connected with the positive terminal and other to the negative terminal through ammeter and switch. This is your temperature sensor, which is the thermometer. It should be dipped, it should be immersed in the water, and there is a stirrer also here. So you need a stirrer here also. Okay, this is the stirrer, for example. Here you have to move it up and down. Okay, all right, this is the stirrer, for example. Throughout the experiment, you have to stir it continuously. This is the calorimeter, this is ammeter, this is water inside the cup, and this temperature sensor goes to the Pascal interface, and Pascal interface is further connected to the computer. So once you are heating it here, the heat energy, the electrical energy is converted into heat energy, and what is the temperature of the water continuously, this sensor is giving the data to Pascal, and Pascal is interfaced with the computer. So you'll see on the screen a graph, temperature versus time. Let's watch this video just for 5 minutes.
Of heat. James Prescott Joule found that the mechanical work done on a system was equal to the heat produced. That is, W is directly proportional to Q, or W is equal to JQ. Thus, Joule's mechanical equivalent of heat is the amount of work that must be performed to produce a unit quantity of heat. Joule's experiment for determining mechanical equivalent of heat. Displayed here is the experimental setup used by Joule to determine the mechanical equivalent of heat. The apparatus used by James Prescott Joule to determine the value of J consisted of a cylindrical calorimeter made of copper. The calorimeter was covered with a watertight lid. Weights were fixed to the inner wall of the calorimeter. Spindle S, carrying a number of paddles, was passed through the central hole in the lid of the calorimeter. The shape and spacing of the paddles was so adjusted that these paddles could rotate in between the fixed vanes. The spindle was attached to a drum and a handle, which could be disconnected from the spindle by removing the pin. The string was wound on the drum as shown here. Joule attached two equal masses at the ends of the string that passed over the pulleys P1 and P2. Two vertical scales S1 and S2 were used to measure the heights through which the masses fell. The temperature of the contents of the calorimeter was measured using the thermometer. The known mass of water M1 was taken in the calorimeter. By rotating the handle, the masses were raised through a height edge. Again, by rotating the handle in the reverse direction, the weights were allowed to fall down through the same height edge. The falling weights rotated the spindle and thereby churned the water contained in the calorimeter. As a result, mechanical work was converted into heat and the temperature of the water increased. The process was repeated. He noted the rise in temperature in each case. By conducting a series of experiments, Joule found that when the falling weights lost 4.186 kilojoule of mechanical energy, the temperature of 1 kg of water increased by 1 degree Celsius. The value of J obtained by this experiment was 4.15 kilojoules per kilocalories. However, the most accurate value is 4.186 kilojoules per kilocalories. Transformation of energy. The potential energy of the falling masses was converted into kinetic energy and finally into heat energy. Click on the link provided to view the modern setup used for determining the mechanical equivalent of heat. Calculations. Let W be the water equivalent of the calorimeter. Theta 2 minus theta 1 degree Celsius, the rise in temperature of water. H the height through which each of the masses fall, and N be the number of times the masses fall. Work done by the masses in one fall is equal to 2 mgh. Total work done is equal to 2 mgh into N. Amount of heat produced, Q, is equal to M1 plus W into theta 2 minus theta 1. Now, Joule's mechanical equivalent of heat, J, is equal to W by Q, that is equal to 2 mgh into N by M1 plus W into theta 2 minus theta 1, that is equal to a constant.
Yes, please. I believe you might have got some good idea for the basic, at least. And let's watch another video, which our colleague, Mr. Timothy, physics instructor, has made it very beautifully. So let's watch it.
Hello. Today we are going to study what we call Joule's equivalent of heat, or the electrical equivalent of heat. We are going to do that using the following materials. First, we have a power supply to supply our voltage and current. We have digital meters to measure the voltage and the current in the system. We are going to use a switch, some connecting cables, a digital thermometer, which we will immerse in our water. We have a calorimeter, which has an attachment which produces heat from electricity using these two coils here. This is our calorimeter, of course, and contained inside the calorimeter is, of course, cold water. We are also going to use our Data Studio software so that we can measure the change in temperature over time. First, you have to get the mass of the water so that we can calculate the necessary values at the end of the experiment. We do that using a digital balance by taking the mass of the calorimeter empty and then filling it with cold water and then taking the mass again. When you subtract the two values, then you can get the mass of the water. Once your water is ready, it's time to connect the circuit. First, we take two cables and we set it aside to be used for our voltage meter. We take another set of cables and we start connecting our circuit. We begin by starting from our power supply, connecting to negative. Now make sure that your power supply is off and the voltage and current dials are set to 0 for safety. From the power supply, we connect to our switch. Again, make sure that your switch is off. And then from the switch, we connect to our digital meter. Because we started from the negative of the power supply, we are connecting the cable to the common terminal of our digital meter. Next, from the common terminal, we will go with the ampere terminal, A. From there, we will connect our heating coils. Now, as I've mentioned earlier, there are two coils, so you have to connect the two coils, this and this, using a short cable. So just remember that the two coils have to be connected in series. We will connect it from this point, or terminal, to this terminal here. Finally, you will take your power supply with the remaining cable, okay, at the positive terminal. That is how you connect the circuit for your current supply. Next, in order to measure the voltage across the two coils, you will take your voltmeter and you will connect two cables. The common terminal, just trace the power supply where the negative terminal is. Connect the common terminal of your voltage. Where the positive terminal from the power supply is, connect the positive terminal for your voltage. Now your circuit is complete. You can now take the temperature sensor and place it inside or in the center of the cover Push it down gently, but not too much. And then finally, you can take your cover, the electric portion of your calorimeter, and gently place it inside the water. You have these two springs to make sure that you can actually lock and seal the inside environment of your calorimeter to prevent or reduce energy from going in or escaping into the environment. Now it's time to make the measurements. First, you have to make sure that you have the software ready on your desktop. Temperature will be on the y-axis and time on the x-axis. Next, with the switch off, turn on your power supply. The switch is located at the back. Push the voltage, you can go maximum. It is safe as long as the current is at 0. And then switch on your switch. There you go. You should get a small amount of current from your power supply, since your power supply current is set to 0. And you should get a small amount of voltage as well. The next thing that you can do is to increase the current so that you will reach up to 1 ampere. You can go up to 2 ampere in order to increase the time it takes to achieve the desired temperature. Once everything is set, go to your software and click start. And from there, it's just a waiting game. You have to make sure though that you should take note of the voltage and the current at the beginning, as well as the initial temperature. You will see that the graph for temperature versus time will be recorded every 15 seconds. That is because by taking a regular time interval, we can smooth out the line and reduce the errors once we take the slope of the graph. Let us fast forward the recording of the temperature. Now that we have reached an ideal temperature, we can stop the recording of the experiment in our Data Studio software by clicking the stop button here.
Also, don't forget to turn off the switch to cut off the power to our circuit. Next, we want to find the slope of the graph that we have of temperature versus time so that we can calculate, based on our equations, the Joule's constant 4.184. We do that by highlighting a straight line portion of the graph. Now, most of the graph looks straight if you do fit and linear fit, but the best way to get the data is from towards the end of the graph. That is because towards the end of the graph, the temperature for the water was given enough time for the temperature to equalize or normalize. Let us take the slope with the value that is displayed on the screen. Also, do not forget to record the final temperature of the water in your data sheet. From here, you can take a screenshot of the graph so that you can submit it with your report.
Yes, please. What's the idea, the theory behind this experiment? Whenever we apply potential difference to any conductor, any metallic conductor, we have electrical energy in that conductor, and that is converted into thermal energy. Thermal energy mean heat energy. Therm mean heat. Right. The heat energy generated in the resistor. Keep in mind that any type of electrical or electronic component has some sort of resistance through the to the flow of the current through the circuit. So heat is directly proportional to the resistor and square of the current flowing through that and the time. If you have more and more time for heating, heat generated will be having large value. Similarly, if you increase the current, you'll be having great amount of heat energy generated. This relationship is called Joule's heating law. If you look at the circuit we already discussed, we have a resistance R of the heating element. We have the potential difference V across its two ends. And whenever we connect the conductor with the battery does work on the charges. It make them flow in the circuit. That work done or heat energy, that work done W or the electrical energy, okay, is converted into heat energy. Don't be confused between this Q charge and the Q heat energy, okay? This is the charge and this is the heat energy, okay? This is the heat energy and this is the electrical energy. Okay, so work done is equal to V potential difference multiplied by the charge, and we know that the flow of the charges through some conductor in time delta t is called I. If I take this time on the left side, so you would get, Q or delta Q is equal to I. The I is the current flowing through the circuit, T is the time. So instead of Q, I can write I multiplied by T. So you will get this one here. This is your heat energy and this is your electrical energy. We have a heating system to study the relationship between the electrical energy and the heat energy. We call it calorimeter. The energy gained by the water. So water is getting energy. So energy gained by the water because it is getting energy, heat energy from the electrical energy of the conductor of the heating element. So Q is the heat energy, MC delta T. This is the charge, okay? This is what I have written here. Okay, so this is the charge. Please correct it. This is the charge. Q is equal to IT. And IT, I write it here. So this is here. And this is your, heat energy. Okay, this is the heat energy. MC delta T. What is M? M is the mass of the water inside the cup of the calorimeter. T is the specific heat of water. You will be taking it as standard 1 calorie per gram per degree Celsius. Okay. And delta T is the difference in the temperature, change in the temperature, which is equal to final temperature T2 minus initial temperature T1. As I told you that the unit for measuring the heat energy is calorie. And we define it as the quantity of heat energy which must be added to a system or removed from it. When 1 gram of water, you have the mass of the water 1 gram, and you change the temperature through 1 degree Celsius. The standard value for Joule's constant is this much, and you will calculate with the help of your readings. This is the voltage potential difference. This is the current. This is the total time taken to convert the electrical energy into heat energy, time in second, current I in ampere, V potential difference in volt, divided by Q, which is MC delta T, M in gram, C in calorie per gram per degree Celsius, and delta T in Celsius. Now, we ignore that the heat absorbed by the calorimeter, so we assume that the total electrical energy is being converted into the heat energy. We assume that the calorimeter doesn't absorb any heat energy. If we draw a graph between, this T and this time, and this is the temperature. So you will be getting like this one. You'll find the slope. And this slope here, M is the mass of the water, C is specific heat capacity, V is the volt potential difference, I is the current. What is the procedure for doing this experiment? To connect the circuit, as we have discussed already, first of all, you have to measure the mass of the calorimeter. Okay. Then fill it up to 2/3. 2/3 mean if you have this calorimeter, for example, and 1, 2, 3, so you fill it up to here 2/3. Why we fill it 2/3? Because just for the safety, because you have a heating element inside. If heating element above the water surface, it is not immersed, it is not dipped into the water. Once you turn on, it will burn out, like sahan at your home. I mean, the geyser at your home. If it is running without water, it will burn out. Similarly, you have a stirrer and you have a thermometer inside. All should be in the water. Open the program Joule's heat equivalent from your desktop. Fix the current nearly 1 ampere from the power supply. Switch on the circuit key and click the program starts. Once you start, you will see a graph. You will see different points, and then if you select join all points, you will see a line. Keep on stirring continuously, because if you stop stirring, you will not get a straight line like this one. So you will be having like zigzag. Sometimes it's going up and down. Okay. You note the temperature T1 and note the average value for the voltage and the current in the table during the experiment. So after reaching some fixed temperature, you can fix it like 35 or 45, whatever you want. Then you switch off and then select the points which are exactly in straight line, and you press fit, and from the drop down menu you click linear fit. It will give you the slope. Okay, then total time in seconds you have to note. And please don't sleep while the teacher is teaching you. Every time, once I finished, after that there is a bombardment on the email and on the WhatsApp. Teacher, do we have this table? Teacher, do we have that table? Gentlemen, it's not good. Many students, they were asking and sending the WhatsApp messages to their friends. This table is there or not? Gentlemen, look carefully. Be in the classroom virtually and study and listen properly. Now we are going to give you the data. We have done experiment in the lab, and I'm going to give you the data, and you will be doing by yourself remaining calculation. It's easy experiment, by the way. First of all, what we do, there is nothing in the calorimeter cup. We measure the mass of the cup. What we did, it's with me, gram. Then we fill water 2/3. So mass of the cup plus mass of the water, I have 80.2. Then mass of the water, M, is equal to minus M. So you do the calculation, and this is 27.6 and this is 80.2 gram. You will subtract it and write down here. Voltage and current, we have already noted. Voltage is 6.334 and current is 0.616. And initial temperature, I have 13 degree, and final, I have 46 degree, for example. Please complete this page, then I will go to the next page. Yes, please. Let's move further. The slope we got, what you need to do, as I told you, and you have seen in the video also, that you have to select the points in the straight line and press fit and then linear fit. It will give you the slope. Slope we got is 0.0159. This is the slope. And you have voltage, current, you have M, you have C, and you have slope. So please calculate Joule's coefficient at Joule constant, and take 5 minutes and complete it, please.
Mister,
Yeah,
I don't know how to find I.
I already told you, gentlemen. You were sleeping, sir?
No, I wasn't asleep, but I just forgot it.
No. You should not forget. You should open your eyes.
Okay.
Just need to open your eyes and شوف بالعينك.
Oh, okay. Okay.
At least you need nothing, just to open the eyes. I'm sorry.
Okay.
Please.
Sorry. Thank you, teacher.
Welcome. Yes, finished.
Yes, teacher.
Good, good.
Yes, teacher.
So what is the value you calculated? Yeah.
It's 8.891.
8.891.
891.
8.891.
Teacher,
Valid.
4.
Yes.
4.
Exactly 4 ولا غير.
4.67.
And the people who are saying 8, they should do it again, please. 4.67.
7.
Huh?
Yes.
V how much?
6.334. Yes.
Mass how much?
52.6.
Okay. And C how much? 1.
1.
And slope 0.0159.
159.
Okay. Right. Then please find the percentage error. Find the percentage error, take 2 minutes, and then we will proceed further for sources of errors and precautions. Yes, please, finished?
Yes, teacher.
What is the percentage error?
I get minus 11.
Oh, you are really great. Why minus?
It is correct, teacher.
Why minus? أنت ما في شوف؟ Absolute مطلق؟
4.184.
No. Why minus? أنت ما في شوف؟ إشارة مطلق. Absolute value. Value?
Teacher, my answer is not minus.
Got it? Yes or no?
Oh, man.
Get it?
Yes, yes, teacher.
Thank you. Should be positive. 11% or ما في
11.6.
11.6.
11.49.
Okay, خلاص 11.6%. Okay, خلاص. Right. Next. Sources of errors and precautions. You see, why you don't have 0% error? Why not the same value as the real one due to many sources of errors? For example, your calorimeter is not perfectly tight. It is still going out of the calorimeter. Okay, so the precautions, calorimeter must be held carefully. Water used for conversion of energy must be pure, because the real value 4.184, we are giving you the Joule's constant for the pure water. If there are some other impurities mixed in the water, of course you cannot trust that value and I mean that water, because it's not pure. Heating resistance must be completely immersed, must be completely dipped in the water, as I told you in the beginning. And if it is not immersed properly, it will not, the temperature sensor will not give you the correct reading, because heating is not that much, because it is above the water. Okay. During heating, water must be stirred regularly. If, as I told you, if you don't stir the water continuously, you will be having wrong graph. That's all. Any question, please?
Teacher, what about source of error?
I told you. Source of error is, for example, the calorimeter is not perfectly tight. And precaution is calorimeter must be held carefully, right? But again it is not perfectly tight, so a little heat can go out of the calorimeter. Okay. Similarly, there might be some the mistake in measuring the mass of the water. There might be some connection errors mistake in the circuit diagram itself. And also another source of error is that you are not stirring water regularly, continuously. Okay, these are sources of error, and precautions are written here. Any question?
No, teacher, thanks.
Thank you very much. Yes, please.
Teacher, can you say the sources of errors, because I didn't hear you clearly.
Actually, sources of error and precautions are vice versa. This is precaution that you should write properly, and if you source of error is that it is not tight, calorimeter is not perfectly tight. This is source of error, and precaution is this one. Okay, the source of error is the water is not pure, and what is the precaution? Use the water pure. Okay, the source of error number 3 is your heating resistance is not in the water. What is precaution? It should be dipped in the water. Okay.
Okay.
Now, fourth source of error is you are not stirring regularly. What is the precaution? Stir it regularly. Okay. Any other question?
No, thanks.
Thank you very much, and have a nice day. And please, I need only report one PDF, whether you have 5 pages, 6 pages, only one PDF. Many, if you submit many pictures and all these things, not accepted. Only PDF at the right place in the folder. Wrong folder, 0. Pictures, 0. Only PDF 1 at the right place. Okay?
Okay, teacher.
And have a nice day.